Kinetic energy, work energy theorem, section 5.4 and 5.5. On the worksheet, do number 1, 2, and 4. Okay. Now, this, I know that sounds really advanced, like work energy theorem. Well, all it says is that energy is needed to do work. Now, I'll give you a non-metric example. Well, I'll put it in with what we've done now. So, like, whenever you calculate work, like you say, if I push a block across the floor, push a heavy refrigerator across the floor 10 feet, and the refrigerator weighs like 200 kilograms or whatever. It won't weigh that much, I don't think, but just say it did. That'd be pretty heavy. 200 kilogram refrigerator, we push it across the floor and it does work as you do that. Well, you might do 3,000 joules of work pushing it down a long hallway. 3,000 joules. Well, that's a lot. Well, to do 3,000 joules of work, you had to have in your body, and to power your arms, you had to have 3,000 joules of energy. So energy is what we need to do work. Now you can kind of understand that the definition of energy is the ability to do work. So calories is what we use in the non-metric. So in other words, if you eat a 200 kilogram, no, that's 400-pound chocolate bar or whatever. If you eat like a 200 calorie chocolate bar, well then now in your body, theoretically, you could now do 200 calories of work. So calorie measures work, just like joule. Calorie is just the English version of it. That there's a foot and yard and feet are the English version, or the English unit, and joule, kilojoule, would be metric. Well, calorie is English, British system, but joule is metric system. Okay, well anyway, I don't know if that helped you or not. But so here it says, this section 5.4 just talks about energy. And the first thing we'll talk about here is kinetic energy. In fact, 5, 3, 5, 4. Yeah, it looks like I don't know why I put the equation later on. Oh, I see what happened. I did a little problem for you. It says a 350 kilogram sledgehammer was moving at 5 meters per second towards a stake in the wall. After driving the stake a distance of 0.210 meters into the wall, let me see. The sledgehammer came to rest. I'm looking at two problems at once. Calculate acceleration, the force on the stake by the hammer, and the work done by the stake on the stake by the hammer. Okay, so, yeah, I guess I'll go on and do this problem out for you. I'll show you. 3.50 sledgehammer. So, a sledgehammer has struck like a big, has struck some kind of a stake they're nailing into the wall, I guess. Well, hopefully be more, we don't want to do the angle thing here, so we'll just kind of do it like that. So this, you hit it like this. That looks really weird looking, okay? But you hit a stake in the wall. This metal, whatever, giant thing. I don't know why you would be nailing it into a concrete wall or whatever it is. But you knock it into the wall. And it says it was moving 5 meters per second. All right, so that's the initial velocity was 5 meters per second. Now, it says that as it struck the stake, it caused it to go into the wall a distance of 0.210 meters. That's your distance that it went into the wall. And it came to rest. That means the final velocity was 0 meters per second. Then it says it weighed 3.50 kilograms. I guess I could do a better job of that. I know, I can draw a little bit better if I take my time. It kind of looks like a sledgehammer, but anyway, 3.50 kg is the weight of this thing. And, okay, we got all the stuff. So first it says calculate acceleration. I'm going to show you a way to do this that we did from past chapters. I'm going to show you something really neat about this. So from past chapters, we'd say, well, acceleration is the final velocity minus initial over time. We don't know the time, but we also know the acceleration is v final squared, the initial plus 2a delta x. So v final was 0. Your initial is 5 meters per second. Don't forget to square it. 2 times A times 0.210 meters. Now, why am I doing this problem? Well, I'm going to show you how it relates and something that ties all this together. 25 plus 0.410 A, 2 times 0.210. So, negative 25. My chalk is having a problem. Equals positive 0.410 A. It's a negative acceleration because it came to rest. It went, it came to a stop. 410. So 25 divided by 4. And it says 60.9. Wow, that's a big number. 60.9 meter per second squared is the acceleration. Let me make sure that's right. So 525 divided by 2 divided by 0.210. Wait a minute. 25 divided by 2 divided by 0.210 divided by 2 again. Oh, I did this wrong. Hold on. 25 divided by 0.410, 60.9. No, I guess I did do it right. What a weird thing. Yeah, it looks like that is right. Okay. All right. Now, I almost typed the wrong number. B, calculate the force exerted on the stake by the hammer. So the force is going to be the mass times acceleration. So the mass of the hammer was 3.50 kilograms, and the acceleration was negative 60.9. I'm still hoping that I didn't do anything wrong here on math. When you're there with me, it's easy. When I'm there in person, live, it's like, oh, Bella, you forgot to do that, you forgot to do that. All right, V final is 5, right? I double check my math. V final is 0. V initial is 5. V squared final, Z squared is 5 squared 25 plus 2 times A, the acceleration we don't know, times 0.210 is the distance it went into the wall, right? Yes. So it is 25 divided by... Yeah, that looks like it's right. Okay, now, the last one, C, calculate the work done on the stake by the hammer. So the work is force, am I doing okay? Yeah, times the distance, parallel force, and we'll just say hit it straight on. So it was 213 newtons, times the distance of 0.210. So 213 times 0.210. Okay, 44.7 joules of work were done. Okay, now, here is the interesting thing. Why did I want to go through that? I was going to show you... Okay, here's what I want to show you something kind of interesting. All right, if this thing was moving, okay, we went through all these steps to get 44 joules. Now, the sledgehammer was moving. It had to have energy to do that work. The equation on the next page you'll see for energy, it had what's called kinetic energy. Now, kinetic energy is an energy an object has because it's in motion. Now, translational, I'll tell you about that word in a minute. If an object is moving, like this thing's moving around, it has the ability to do work. Energy is the ability. Because it could, like, this could strike my hand and maybe make it move over, okay? We'll just do that, or strike an object. It's better if I did something like this. Yeah, I can do it this way. I can show you a real example. So here's, all right. So this calculator, if I slide it across, it has, all right, it has the ability, it did move it a little bit. It has the ability to do work. It wasn't too great. I'll try it again. I'll do it this way. Watch. It has the ability to do work on the marker. Now, it didn't, I'm kind of holding it, but it didn't because it didn't hit the marker. But it still had energy. This had kinetic energy. It has the ability to do work. Now, this time, we'll see if I can be more successful and actually let it do work. So, if it does work, yes! All right, it translated its energy. It translated into work done on this, okay? And for that matter, work done sliding against friction. There's a little bit of friction here with that. So, energies need to do work. It should be equal. So, if the sledgehammer did 4.7 joules of work, it had to have 44.7 joules of energy. Kinetic energy is equal to 1/2 times the mass, which is 3.50 kilogram, times the velocity squared. It was moving at 5 meters per second. So the definition is, if all of this energy, if it completely comes to rest, and it means it goes from 5 to 0, it should have the same amount of energy. So that will be 25 times 3.50 divided by 2, and I get 43.8 joules. Now, those numbers, they should be equal, but of course we went through a lot of steps and rounding and this and that in there, and hopefully I didn't make an error on it, but they're really close. They're pretty much 44, just about 44, about 1 apart. But they're the same, so they should be the same. So kinetic energy, this is a lot easier than doing all those steps I just showed you, isn't it? Yes, it is. Yes, it is. Okay. Well, the work energy theorem just says energy can be converted into work, and actually work can even be converted into energy in some other cases. I'll show you that as well. So let's go to the next page, and we'll use that. And that's what I was telling you about. I probably should have started off on the next page. Energy is the ability to do work. Kinetic energy is the energy that an object has due to its motion, and it can translate to another object. We call it translational kinetic energy. That just means if it's kinetic energy that is used, if the full kinetic energy is exerted on the stake or on another object, you'd know it because that means it stops. It goes from, it's moving, but then it comes to a stop. You've exerted your full kinetic energy. If you run into somebody, you play football, whatever, you're running, you're blocking them or whatever, if you run into them with your full energy and you knock them down and you both of you stop, you come to a stop somewhere on the ground or wherever, or even sometimes it's standing up, you'll see people holding players against other players. But if you completely come to a stop, then you have given all of your kinetic energy to that collision. Okay, letter A says, a 15 kilogram bowling ball is flying through the air at 18 meters per second. How much kinetic energy does it have? Well, this is pretty easy. I almost don't need to do this example, but so it says 15 kilograms is the mass, 18 meters per second. So if it comes to rest, it can do 18 squared times 15 and then divided by 2. It can do 2430. That's a lot more than that hammer. So you don't want somebody throwing a bowling ball at you. I can tell you that won't be too fun. It'd be hard to throw it even too, but if it were, that's a lot more work it can do on you. B, how much work must be done on a 15 kilogram bowling ball to accelerate it to 25 from rest? All right, how much work? Okay, so work is equal to the change in kinetic energy. Now this actually comes in the next page. On the next 5.5, that's why I put these together. Section 5.5 says, the net work done on the object is the change in kinetic energy. Now change in anything is always final minus initial. So I guess I better put it up here because I'm going to run off the board there. Actually, I don't even need that part up there. All right. The work done, and according to the work energy theorem, is a change in kinetic energy. Now, in math, in chemistry, anytime you see the change in something, delta, the triangle, well, look at the triangle, but it's letter D in Greek, it means the final minus the initial. So that means final kinetic energy minus the initial kinetic energy. So, if it says it's moving at 25 meters per second, and it accelerates to 25 from rest. So that means it started at 0. So 1/2 mv squared initially was 0, and then 1/2 mv squared. If you want to put final and initial, you can do that as well. Okay, so the final velocity was 25, so 1/2. And it said it was 15 kilogram. And the final velocity was going to be 25. And you're going to square it. Minus, now you'll like this, if you start from rest, that makes the math pretty easy because look at this. 0! You get to square 0, and so that becomes nothing right there. But see, you could say, what if you accelerate, if you want to accelerate, now think about way back to the first chapter or last semester, okay, you're pushing a cart that weighs like, I don't know, 100, 200, 50 kilogram cart, like a shopping cart. And you want to accelerate it from, just say you're already moving from 2 meters per second to 20 meters per second. You want to accelerate from there to there over a distance of 20 meters. How much work will you do will be done on that? You go through all the steps like I just showed you a moment ago. It's a long problem. You go, oh, this, like I did at the very beginning of this lesson. But look, you don't have to do that. You can also do it this way. If you know the initial and final velocity, you'll find the work done right here. And so, let's see, 1/2 times 15 times 25 squared. It's 625 times 15 and divided by 2. 4690 joules and minus 0, so you don't even need the other one. So 25 squared times 15, then divide by 2. There it is. Yeah. Okay. Now, as I showed you on the work, you're only going to do number 1, 2, and 4. I put these two sections together. So let me show you. There's a couple more problems. I might do both of them, and if you wanted to stop the video and look at the problem, and say, oh, you might already be able to work them out right now. Some of you might be already. You don't need to see all this. I think I've kind of done it. In fact, here's a shopping cart problem. Lena accelerates a 20 kilogram shopping cart. There it is, from 4 meters per second to 9 meters per second over a distance of 12 meters. How much work was done on the cart? What force in newtons was applied to the cart? Okay, so how much work was done and what force was applied? 20 kilogram, it went from 4 to 9 meters per second. Okay, so I'll do the work had to equal kinetic energy final minus initial kinetic energy. So that would be 1/2 mv final squared minus 1/2 mv initial squared. So this time a little bit more math involved. The 20 kilograms final is going to be 9 meters per second. I got to square it. And the initial was 4 meters per second. Okay, so let's get the calculator here. Yes, calculator, right? 81 times 20 divided by 2, 810. Minus 16 times 20 divided by 2, 160. Wow, it's amazing because as you increase your velocity, so you're squaring the effect on the work. So if you increase your velocity, it exponentially increases. 4 to 9, look at that, 810 to 160. So I'll just double check it. 4 times 16 times 20 divided by 2. Yeah, that makes sense. Oh yeah, that makes sense. That will be like times 10. 1/2 of 20 is 10. Okay. All right, so 810 minus 160 is 650. I guess I could have done that without a calculator. Okay. All right, so this is how much work was done on the, I'll put W in fact, W, not to put the whole, but this is how much work was done on the shopping cart. Now, to find out B, that was A, B, what force in newtons was applied to it? So this was A part A, and then A part B would be, well, if work equals force times distance, you assume she just pushed it straight ahead. So 650 joules equals the force that was applied times how far did it go? It went 12 meters. So you just divide both sides by 12. 650 over 12. And it's 54 point, well, maybe just 50. Well, yeah, those could actually have 3 sig figs. 54.2. And I don't really do much with sig figs with you guys anyway. But in my AP Chem, I do it all the time, and I have to. So I kind of just can't help it. I got to keep thinking about that. 54.2 newtons would be the force. There it is. I mean, if you really want to do units here, you don't have to do this, but joule is equal to a Newton dot meter. So if you're dividing them both by meters, meter, 12 meters, well then the N is left over, so that's how you get your newtons. All right, so this is a neat little thing, and let's see if there's anything different. Like I said, you probably could just jump on to the next problem. Oh, okay. It looks like this is the same problem, but I just kind of worded it in a different way. So yeah, I don't know if I have to do this whole thing. It says, what if Lena accelerates a 20 kilogram shopping cart from 4 to 9? Oh, 4 to 9. Oh yeah, same thing. By a 54.2 Newton force. How much work was done? And what distance did the cart travel? All right, so it's the same problem. So the work done, it was 650, right? So it's the same number, 650. What distance did it travel? So all we're saying here is, if we were to give you, so on B, it's the same problem as A. The first part's the same. It's the same problem actually. But I just said, but notice they did not. Here they gave you for this part, they didn't give you the distance. They gave you the 54.2, which was the force. They gave you the force, but not the distance. And of course, you just found 650 joules. So then you would just divide that. So it's just all we're doing here is showing you, like I said, some of you could probably just, oh, you're ready now, I hope. If not, you can go back through and watch this. But it's the same problem. Everything will be the same. You'll do changing kinetic energy, 1/2 mv squared final minus 1/2 mv squared initial, and you'll get 650. So work equals change in kinetic energy. Do the same thing you did on the problem A, and you get that number. Now it says, if they had not given you the distance, but they gave you the force, what would be the distance? So then you divide by the force on both sides. 650 divided by 54.2, and that gives you 12. Okay, and that was correct, wasn't it, from the last problem? 11.99, yeah, 12. Okay, so 12 equals the distance. All right, so just do those 3 problems, and hey, we're close to being done with this. There's a couple of neat things left in the chapter to show you. Probably just 2 or 3 more lessons at the most. All right, see you guys later.